Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to the Power and Electronics lecture series at Concepts Abatabad. In this lecture, we shall discuss the single phase to single phase, three phase to single phase, and three phase to three phase step down cycloconverters. Cycloconverters. A cycloconverter is a frequency changer that converts AC power at one input frequency to AC output power at different frequency. There are two types of cycloconverters. One is called step-down cycloconverter, in which the frequency of the output signal is lower than the frequency of the input signal. The other type is called step-up cycloconverter, in which the frequency of the output voltage signal is greater than the frequency of the input signal. In the previous lecture, we have discussed the step-up cycloconverter by using midpoint topology and bridge type topology. In this lecture, our focus will be on the step down cycloconverters by using midpoint topology and also for the bridge type topology. And also we shall discuss the three phase to single phase step down cycloconverter and three phase to three phase step down cycloconverters. In this slide, we shall discuss the single phase to single phase step down cycloconverter by using midpoint topology. Figure 3a shows the circuit diagram of a single phase to single phase cycloconverter by using midpoint topology. Our objective is to achieve an output signal of a frequency lower than the input signal frequency. So here the frequency of the output signal is half of the frequency of the input signal. So how we can achieve this? Let's see the operation of the circuit shown in figure 3a. In figure 3a, the SCRs T1 and T4 belongs the SCR T1 and T3 belong to the positive group, means we are getting the positive voltages and current of the output signals, and the SCRs T2 and T4 belongs to the negative group. So let's see the operation of this circuit, how it will work. For the positive half cycle of the input signal, we have polarity like this at the input side. So for this polarity, the SCR T1 is in the forward bias direction. We need a gate pulse to turn on this device. So at omega t equal to alpha, we trigger the SCR T1 and the current starts flowing through the T1 and through the load, and we have the path for load current like this, and we are getting the output voltage waveform like this, which follows the voltage VAK, and also the output current, and we trigger the SCR T1 at omega t equal to alpha is like this. So at omega t equal to pi, the polarity at the input side is reversing its direction, and we are getting this polarity, negative and positive. Now we know that the point B is more positive with respect to point K and A, and the point K is more positive with respect to point A only. So for this polarity at omega t equal to pi, the SCR T1 is line commutated and the SCR T3 is triggered at omega t equal to pi plus alpha. So the load current will start flowing, and it has a path like this, and we are getting the output voltage, which again at the positive side, and also the load current shaped like this. So at omega t equal to 2 pi, the one complete cycle of the input is completed, and we are getting two half cycle at the positive side of both the output voltage and the output current, like this. So at omega t equal to 2 pi, the again polarity at the input side reverses its direction, and we are getting polarity like this, positive and negative. So at omega t equal to 2 pi plus alpha, the SCR-T3 is line commutated. At omega t equal to 2 pi, the SCR-T3 is line commutated, and we trigger the SCR-T4 at omega t equal to 2 pi plus alpha. So for this polarity, we triggered the SCR-T4. How? As we know that the point K is more positive with respect to point B, and the point A is more positive with respect to point K and B. So point K is more positive with respect to B, and the load current will flow like this and through the SCR T4 like this, and we are getting the output voltage, which is the opposite of the output polarity we have marked earlier, and the output current will be like this. We can clearly compute the polarity and the direction of the output current and the output voltage by applying the Kirchhoff voltage law and current law for each interval of the in which the SCRs is in the conduction mode. Means as T1 is conducting from alpha to pi, and T3 is conducting from pi plus alpha to 2 pi, and T4 is conducting from 2 pi plus alpha to 3 pi. So at omega t equal to 3 pi, the polarity at the input side again changes its polarity, and we are getting this polarity at the input side. Now the point B is more positive with respect to point K and A, and the point K is more positive with respect to point A only. So for this, at omega t equal to 3 pi plus alpha, we triggered the SCR-T2, and the current through the load flows in this manner, and we are getting the output voltage like this and the output current like this, and T2 will conduct from 3 pi plus alpha to 4 pi, and after 4 pi the third cycle of the input signal starts, and we are having the same procedure as we discussed for the previous two cycles. We can also compute the average output voltage, which is a dotted line, and also the average output current, which is again a dotted line, and we can clearly see that for the two input cycle of the input signal, this is the one complete cycle and this is the second cycle. So for the two input cycle of the input signal, we are having one cycle of the output voltage and output current. In other words, we can say the time period of the output signal is twice the time period of the input signal. So we can define the time period of the input signal, so which is this one, T1, and the time period of the output signal is this one. So we can summarize that we are achieving an output signal having frequency lower than the input signal frequency. So this was the single phase to single phase step down cycloconverter by using midpoint topology. So in this slide we shall discuss the single phase to single phase step down cycloconverter using bridge type topology. Figure 4a shows the circuit diagram of a single phase to single phase cycloconverter with bridge type topology. Again, our objective is to achieve an output signal of a frequency lower than the input signal frequency. Here the frequency of the output signal is the half of the input signal frequency. So let's see how we can achieve this and how the circuit shown in figure 4a will work to achieve our desired objective, which is to obtain an output signal of a lower frequency than the input signal frequency. So for the positive half cycle of the input supply, we know that in figure 4a the SCRs from T1 to T4 belong to the positive group, and the SCRs from S1 to S4 belongs to the negative group. So for the positive half cycle of the input supply, we have polarity at the input side like this. The point A is positive and the point B is negative. So at omega t equal to alpha, we triggered the SCR T1 and T2, and the current starts flowing through these devices like this, and which is the path of load current, and we are getting the output voltage like this and the output current like this. At omega t equal to pi, the polarity at the input side reverses its direction, which is negative and positive. Positive and negative, and the SCRs T1 and T2 are line commutated at omega t equal to pi, and we triggered the SCRs T3 and T4 at omega t equal to pi plus alpha. At omega t equal to pi plus alpha, we triggered the SCR T3, and it will start conducting, and the load current will flow like this through through the T4 and goes back to the source, and we are getting the output voltage like this. It follows and we can clearly compute the output voltage by applying KVL and KCL and ignoring the drops across the SCRs. So at omega t equal to 2 pi, the SCR the SCR T3 and T4 are line commutated, and we triggered and the polarity of the input signal reverses its direction, and we are getting this polarity at the input side, which is positive and negative. And again at omega t equal to 2 pi plus alpha, at omega t equal to 2 pi plus alpha, we triggered the SCRs S1 and S2. We triggered the S1 and it will start conducting. And the current flows through the load like this through the S2 and goes back to the source like this. Clear? And we are getting the output voltage like this and the output current like this. So we can say that the conduction period for the SCR S1 and S2 is equal to 3 pi plus alpha minus 2 pi plus alpha. So at omega t equal to 3 pi, again the polarity at the input side reverses, and we are getting the negative half cycle of the input side, which is negative and positive. The point A is now negative and the point B is positive. And again at omega t equal to 3 pi, the SCR S1 and S2 are line commutated, and we triggered the SCR S3 and S4 at omega t equal to 3 pi plus alpha. At omega t equal to 3 pi plus alpha, and the load current will follow this path, and we are getting the output voltage like this. And we can clearly see from the figure B, the average output voltage will be like this, and the average output current will be like this. So we can say that for the two cycle of the input signal, we are having the one complete cycle of the output voltage and current. So this is the one complete cycle of the input signal, and this is the second complete cycle of the input signal. So for the two input cycles of the input signal, we are having the one complete cycle of the output voltage and also the output current. In other words, we can say the time period of the output signal is the twice the time period of the input signal. So the time period of the input signal is this one, which is equal to t1, and the time period of the output signal is equal to this one. So we can conclude that the frequency of the output signal is the half of the frequency of the input signal. So we discuss the single phase to single phase step down cycle converter using break type topology. So in this slide we shall discuss the three phase to single phase cycle converter with RL load. Figure 5 shows the circuit diagram of three phase to single phase cycle converter with RL load. Here in this figure, the ACRs from T1 to T3 belongs to positive group, and the ACRs from S1 to S3 belongs to negative group. Here our objective is to achieve a single phase output voltage with low frequency from a three phase supply system. To achieve an the output voltage at low frequency from a three phase supply, we need to vary the alpha of each SCR progressively. So let's see how this circuit will work and how we get the single phase output voltage at low frequency from a three phase supply system. In figure 5b, this shows the phase A voltage. You can represent it like this: VAN at 120 degree of phase difference. This shows the phase B voltage, which is VBN, and this is the phase C voltage, which is VCN. So to vary the alpha progressively, we need to compute the change in firing angle. So how we can achieve this? Change in firing angle means change in alpha is equal to the reduction factor, which is 1/8 in this case, into 120. So here 120 is actually the conduction angle for the each SCR during the each phase. So we can say that this is the 120 degree and this is the 120 degree, and 1/8 is the reduction factor in the frequency, that how much the reduction of the input frequency we need at the output side. So in this case it is 8. So how we get this? As we know that here this is the positive half cycle of the output voltage, and we have 4 cycles of the input signal for one half cycle of the output voltage. So this is cycle 1 of the input signal, so this is the cycle 2, this is the cycle 3, and this is the cycle 4. So for the complete cycle we have the 8 for the complete cycle of the output voltage we have the 8 cycle of the input signal, which means the time period of the output signal is 8 times the time period of the input signal. So we get the reduction factor in frequency 1 by 8, which gives us 15, right? So now let's see how this circuit will work. So at omega t equal to alpha, and alpha here, alpha equal to 90, we trigger the SCR T1. So at alpha equal to 90, at point A we trigger the SCR T1, and we are getting the output voltage like this up to the point B. So the SCR T1 will conduct, and at point B we need to trigger T2. So for this we need, at what value of alpha we need to trigger T2. So we compute the change in alpha, which is equal to 15, and so at point B, for the alpha for the SCR T2 will be equal to 90 minus 15, which is equal to 75, right? And at point B, the alpha equal to 75, we trigger the SCR T2, and we are getting this output voltage up to C. And at point C, again we need to trigger the SCR T3, but at what alpha? Again the reduction in the progressive value of the alpha will be equal to 60. How we get it? 75 minus 15. Likewise, we are getting the output voltage like this up to the point D, and at point D we again need to trigger the SCRT1, and at what value? The value of the alpha will be 45, like this, and we are getting the output voltage like this. At point E, again we need to trigger the SCRT2, but at what value of alpha, which is equal to 30, which again we get it from 45 minus 15, which is equal to 30. So each time we are negating the 15 degree from the previous value of the alpha for the updated value of alpha. So this is the output voltage at point F. So at point F, we need to trigger the SCR T3, but at what value of alpha? Again the 30 minus 15, which is equal to 15. So at point G, again we need to trigger the thyristor T1, and at what value of alpha? But in this case the alpha will be 0, that the previous value of alpha is 15, so 15 minus 15 is equal to 0. So at alpha equal to 0 we are getting this voltage up to H. So again from point G to H up to the point M, we are progressively increasing the alpha by a difference of 15. So at point H the firing angle will be 15, and again at point M it will be equal to 19. So we are getting the output voltage, the off portion of the output voltage, the average value of the mean value of the output voltage like this. So it has a time period of the so for the complete cycle, the time period of the output signal is the 8th time of the input signal. So it is clearly seen in the figure 5b that from a three-phase supply we are getting the single phase output signal with low frequency. So in the previous slide we have discussed the operation of three-phase to single-phase cycle converter with RL load. Here is the more information for the operation of three-phase to single-phase cycle converter with RL load. We discussed this waveform. The figure 6c shows the complete cycle of the output voltage, and we know that how we can achieve this one. So when the output voltage is negative, we call the process inversion, and when the output voltage is positive, we call the process rectification, which is shown in figure 6d. So also for this period current in positive group, and for this period of the output voltage current is flowing to the negative group of the cycloconverter. Three-phase to three-phase cycloconverter with R load. Figure 7a shows the three-phase to three-phase cycloconverter with Y-connected load. There are 18 ACRs. Each P and N group has 3 ACRs. So each P and N group has 3 ACRs. So there are 18 ACRs for the whole circuit. The P is the positive group of ACRs and N is the negative group of the ACRs. So for the positive half cycle of the output voltage, the positive group of ACRs will be active, and for the negative half cycle of the output voltage, the negative group of ACRs will be active. A care is needed that both positive and negative ACR group cannot be turned on, the ACRs cannot be turned on simultaneously. Figure 7b shows the result of one phase of the output voltage. Here the average waveform of the output voltage will be like this. It can be clearly seen from the figure 7b that the average value of the output voltage is computed by using this relationship, and it has a frequency of one-third of the frequency of the output signal is one-third of the input signal frequency. How? For each cycle of the output voltage, there are 3 cycles of the input signal. So this is the one cycle of the input voltage, this is the second cycle of the input voltage, and this is the third cycle of the input voltage. In other words, we can say that the time period of the output voltage is the 3 times the time period of the input signal, or the frequency of the output voltage is one-third of the frequency of the input signal. So the voltage waveforms for the rest of the phases will be similar to this one. Thank you very much for your patience, and good luck.